Okay, this is 13.3, day 2, video 2. So we've learned a new formula for curvature, which is going to be much more user-friendly. And we developed it in the last video, which pretty much was the whole video. Now we're actually just going to put it to use. So we have already done this one. We've already figured out that the curvature of that circle, a cosine t, a sine t 0, is 1 over a. Well, now we're going to use the new formula just to show that it's actually quite a bit easier to do using our new formula. So remember that the new formula requires r prime and r double prime of t. So let's get those first. So r prime of t is going to be the derivative, which is negative a sine t, a cosine t 0. We need r double prime of t. So the derivative of the first derivative is going to be negative a cosine t, negative a sine t 0. We're going to need to cross those two things. So r prime cross r double prime. The nice thing is it's kind of already set up in the right way. If you kind of want to cheat, like I sometimes do, I'm going to do that. Doing I, J, K on top of those things right there, just to kind of put it in that right form. And then you can do your cross product. So eliminating the I row and column, you're going to get 0 minus 0. Wonderful. Eliminating the J row and column, you're also going to get 0 minus 0. Awesome. Eliminating the K row and column, let's see, we're going to get negative a sine t times negative a sine t, which is going to be positive a squared sine squared t. Subtract or minus a minus, because we're going to get a minus a cosine t times a sine t, so it's going to be minus minus, which is plus a squared cosine squared t. If I were to factor the a squared out of that, we're going to get an a squared times sine squared plus cosine squared, which of course is 1. So ultimately, for our cross product, we get 0, 0, a squared. Okay, then we need the magnitude of that because this is going to be our numerator. So the magnitude of r prime t cross r double prime t is going to be the magnitude, which is the square root of 0 squared plus 0 squared plus a squared squared. So you're going to get basically a to the 4th underneath, which is going to be the square root, and it's going to give you a squared, which really should make sense because a itself really is just a constant. And if you take the magnitude of a constant, it is the constant. So there is your magnitude of the numerator. Now what we need is just the magnitude of r prime of t for the denominator. And we already have r prime of t, so now we just need to take its magnitude, which is going to be the square root of, let's see, squaring negative a sine t is going to be a squared sine squared t. Squaring a cosine t is going to be a squared cosine squared t, and squaring 0 is just 0. So it looks like here we're going to get the square root of, remember you can factor an a squared out of that, so you're going to get the square root of a squared sine squared plus cosine squared, which again is 1. So you get the square root of a squared, which happens to be a. Okay, we've got everything we need now. Curvature formula, the new one, is the magnitude of r prime cross r double prime divided by the magnitude of r prime cubed. So we're going to get a squared over the magnitude of r prime a cubed, which of course reduces to 1 over a. Pretty cool stuff. All right. So now what happens if maybe we have just a 2-dimensional curve? It's not a 3-dimensional vector. So let's just take one in general. Let's just say that r of x is going to be a two-dimensional curve. Well, let's actually sketch this. I've got some kind of a two-dimensional curve here, doing whatever it's doing. We can still create, from the origin, a vector which points to every single point on this curve. And this specific point here is just going to be an x value. And the related y value, instead of calling it y, we're just going to call it f of x, or a function of x. So it's going to have a related x component and a related y component, but since it's in two dimensions, it has no z component because it's going to be basically on the xy axis, so z would be 0. So if we're going to create our r of x from this, it's still going to be a three-dimensional vector. It's just going to be x, f of x, which is the same as y, and 0, because there's no height to this z component. So now we can go ahead and follow through with our formula. R prime of x is going to be the derivative of x, which is 1. Derivative of f of x is f prime of x, and the derivative of 0 is still 0. We're going to need a second derivative. R double prime of x, 0. Second derivative of f, 0. Okay, not too difficult there. We need to cross the two. R prime of x cross R double prime of x. So crossing those two, again, if you kind of put your bars around the R prime, R double prime, put the ijk on the top, hopefully you can see this. We eliminate the I row and column, we're going to get 0. I just noticed that my double prime here in the step above kind of looks like a 4, so I'm going to make that a little clearer. There we go. The j row and column, if I get rid of the j row and column here, I'm going to get 0 minus 0, which is 0. And then if I get rid of the k row and column, it looks like all I have is f double prime of x minus 0, so we get f double prime of x. And then again, if I take the magnitude, while f double prime of x is a function, when you evaluate it at a point, it's a scalar. So again, the magnitude of a scalar is the scalar. So this is just going to be f double prime of x. When you substitute an x value and you just get a number out. Then we need the magnitude of r prime of x. So that looks like that's going to be the square root of 1 squared plus f prime of x squared plus 0 squared. So our curvature is going to be f double prime of x divided by the square root of 1 plus f prime of x squared, but I can write that as 1 plus f prime of x squared. Now the square root, remember I have to cube it, so that really means that whole thing is to the 3/2 power, since I am cubing that square root. Okay, the only other thing that we have to add to this is we're putting an absolute value symbol on the top, because the curvature is going to be a positive value. You could possibly get a negative value out of your magnitude. You really shouldn't, but it is possible when you plug it into a function that you will. And there you go. So this is for a two-dimensional curve. So you'll take the second derivative of the function divided by 1 plus the first derivative squared, all to the 3/2 power. And that's your curvature for a two-dimensional function. So let's go ahead and do an example. Find the curvature of y equals sine of x. Okay, so curvature function is going to be, let's go ahead and find the components. So we need f prime of x, which is going to be cosine of x, and we need f double prime of x. Those are really the only two things we need, which is negative sine of x. So according to our formula, it was the magnitude, or the absolute value, of f double prime of x in the numerator, which is negative sine of x, divided by 1 plus the derivative squared, so cosine squared of x, all raised to the 3/2 power. And that's the formula that you would need to find the curvature of sine of x. Now, depending on where you want to find the curvature, it's obviously going to change. So if you think about it, something at like pi, where sine is kind of crossing through the x-axis, you would think that that would be a relatively small curvature. So let's see. Cosine of pi, I'm sorry, not cosine, curvature of pi is going to be the negative sine of pi, absolute value, divided by 1 plus cosine squared of pi, all raised to the 3/2 power. And of course, sine of pi is 0, so negative 0 is still 0, absolute value of that is still 0. As long as I don't get 0 in the denominator, we're okay. Cosine of pi is 1, so you're going to get 1 squared, which is 1, so 1 plus 1 is 2, you're going to get 2 to the 3/2. Again, as long as that wasn't 0, we're fine. So the curvature at pi is 0. So when the sine function crosses through the x-axis there at pi, it actually has no curvature at all. And then let's try something where we know we will probably have a great amount of curvature, which is at the top, at the maximum of sine, which is at pi halves. So we would do the negative sine of pi halves, absolute value, over 1 plus cosine squared of pi halves, all raised to the 3/2 power. So the sine of pi halves is 1. Negative is going to give us the negative 1, but it is the absolute value, so we get 1 on top. And the cosine of pi halves is 0, so 0 squared is still 0, plus 1 is 1, 1 to the 3/2 is 1, so we ultimately get a curvature of 1. So one thing you should notice is that there is a maximum curvature of 1 and a minimum curvature of 0. You can obviously have curvature in between. If you were to do like the curvature of pi fourths, you would get approximately, I'm not going to write it all out, you would get approximately 0.3849, I think it was. I had that written down. So you're always going to get a curvature between 0 and 1. 0 meaning no curvature, 1 is the maximum curvature, and then anything in between. Okay, we have 3 more topics to talk about for this section. They are T of t, the unit tangent vector, which we kind of already know. So technically it's 2 topics. N of t, which is the unit normal vector, and then B of t, which is the unit binormal vector. So let's go ahead and define these things. So T of t, this is the one that we already know. This one is defined as the unit tangent vector. Again, it's just a tangent vector with a magnitude of 1. And we already know the definition of that one is r prime of t, which is the derivative, divided by the magnitude of r prime of t, which is its length. So if you take a vector and divide it by its length, it gives you the magnitude of 1. A normal, unit normal vector, unit normal vector. Okay, a unit normal vector is just like a regular normal line would be. It's perpendicular to a tangent. So let's say that we have a curve, which, I don't know, it's going to go all over the place, does something like this, and it goes behind itself, and it comes down here, whatever the curve looks like. Ultimately, I'm going to use the upper part of this. So let's say that we have a curve. Right here, we've got some kind of a tangent vector. And we'll just say that it's going in this direction. So we've got a tangent vector which comes off of this curve like that. And we'll say that that's our unit tangent vector. But then we have a normal vector. And the normal vector is going to be perpendicular to that unit tangent vector. So it's going to look something like this. So then the question is, how do we find that? Well, you find the unit normal vector by taking the derivative of the tangent vector, and because we want it to be a unit, we divide it by the magnitude of the unit tangent vector. Okay, and if you remember that the unit tangent vector and dotted with itself is 0 because they're perpendicular to each other. So we're going to recall that the unit tangent vector dotted with its derivative is 0 because they are perpendicular to each other. Okay, and then the last thing is called the binormal. Let's go with purple on this one, I guess. The binormal unit vector, that's this b of t, is a vector which is perpendicular to both the tangent and normal vectors. And if it is a vector which is perpendicular, because it is binormal, normal to 2, normal to both vectors, then it's going to be done by finding the cross product of t and n of t. And that's the binormal unit vector. Okay, drawing that one is not going to be quite so easy, but maybe I can try. Maybe it looks something like this. And the biggest thing here is that it is perpendicular to the normal and it is perpendicular to the tangent. So that's how you're going to find these three things. So really you're going to need, in order to find the normal and binormal, you're going to need the unit tangent vector first. Then to find the unit normal vector, you use that one. And then to find the binormal, you use both the tangent and normal. There we go. All right, let's do an example. For the helix, which is given as cosine t, sine t, t, we want to find all three things. Specifically, we're going to go ahead and find these at a value where t equals 0. So let's add that in there. We're going to find this at t equals 0. Okay, obviously we need to find the unit tangent vector first. So let's go ahead and do that. The unit tangent vector. Unit tangent vector, again, was defined to be r prime of t divided by the magnitude of r prime of t. Again, just remember, tangents are derivatives. The derivative divided by its length gives you a unit derivative vector. So let's find r prime of t. R prime of t is going to be negative sine t, cosine t, 1. The magnitude of that is going to be square root of, that's going to be sine squared plus cosine squared plus 1, which is going to be sine squared plus cosine squared again is 1, so it's going to be the square root of 2. All right, so now in order to find the unit tangent vector, we need to do r prime of t divided by its magnitude, or we can just put the magnitude out front as 1 over square root of 2 times r prime of t. It might be easier in this case to write it this way. Or you could divide each component by the square root of 2. It doesn't really matter, just whatever's easier. And I said we want to find this specifically at 0, so we're going to do unit tangent vector at 0. So that's going to be 1 over root 2. So negative sine of 0 is 0, cosine of 0 is 1, 1 evaluated 0 is still 1. So there is my unit tangent vector. To find the unit normal vector, we're going to need t prime of t. Okay, we already have t of t, so now we can find its derivative. So t prime of t is going to be 1 over root 2. Derivative of negative sine is negative cosine. Derivative of cosine is negative sine. Derivative of 1 is 0. And then we're going to need the magnitude of t prime of t. 1 over root 2 stays there. Again, magnitude of a constant is the constant, times the square root of cosine squared t plus sine squared t. When you square those, they become positive, plus 0. What's underneath the square root is 1, so we just get 1 over root 2. So our unit normal vector is going to be all of the unit tangent vector prime divided by the magnitude, which is 1 over root 2. The 1 over root 2s are basically just going to cancel each other out, which is awesome. So the normal vector is just going to be negative cosine t, negative sine t, 0. All right, we're on a roll. Let's go ahead and find this at 0 because that's what we wanted to do from what I added in. So negative cosine of 0 is negative 1, negative sine of 0 is 0, and 0. Okay, last thing we need to find is the binormal. The binormal, once again, is defined to be the cross of the tangent vector and the normal unit vector. So we are going to get I, J, K. I guess I will have to distribute the square root of square root of 2's on this one just to make it easier. Could actually pull it out to the front, but probably easier this way. So the unit tangent vector is going to be negative sine t over root 2, cosine t over root 2, 1. And then the unit normal vector is going to be negative cosine t, negative sine t, 0. All right, let's go ahead and do our cross product. So if we eliminate the I row and column, we're going to get 0 minus negative sine t, which is going to be, oops, I forgot something. That should be divided by root 2. It's going to be negative sine, so it's going to be 0 minus negative sine t times 1 over root 2. So it's just going to be sine t over root 2. Eliminating the j row and column, we're going to get 0 minus negative, so that makes it positive cosine t over root 2, but don't forget to change the sign, so that one should become negative cosine of t over root 2. And then the last one, eliminating the k row and column, is going to give us a positive sine squared minus minus, so plus cosine squared over root 2, which is going to be a 1 over root 2. So that is the binormal vector. And then we want to find the binormal vector at 0. So plugging 0 in, we're going to get 0. Looks like negative 1 over root 2, 1 over root 2. And you could always double check to make sure that this is indeed the case, because if you take two things which are perpendicular and dot them, you should get 0. So if I take the binormal vector that's given here and I dot it with the normal vector, it should be 0. If I dot it with the unit tangent vector, it should be 0. And if you dot the normal vector with the tangent vector, that should also be 0. And all of those things do work out. I'm not going to walk through all of them, but they all do work out. So there you go. That is the concept of the unit tangent vector, unit normal vector, and the unit binormal vector.